Good afternoon, all. In this session, we are going to uh, have two sessions in this 1 hour, half an hour each. Dr. Jahir Nabi will be speaking on how to construct the forest plots, and Dr. Partapal will be speaking on how to draw the Kaplan-Meier survival analysis. So these are two important sessions, and if any questions you have after the end of the session, we can ask. Please carry on.
Visible. So, good afternoon, all. Not a very difficult topic to learn. Forest plots, principles, and practical demo. So, this talk will be divided in two parts. First will be like how to read a forest plot, what are the different components, and the second will be how to make a forest plot. So, I'll be demonstrating it using one of the softwares, which is quite easily available online. So first of all, forest plot. What is a forest plot? It's also called a blobogram, but it is not a very commonly used term. And it's a graphical display of results from a number of studies. So you have number of studies, each showing some different results. Now you want to know that how to interpret all these different studies. So it's a graphical display of all the estimated results, and then finally a pooled results. The overall results will give you an idea that which way the results are going, if there are suppose different results in different studies. So what's the exact spelling of forest plot? This is somewhat very amusing. So people have used both the spellings, forest, single R, double R. So the actual spelling is single R because this represents the forest. But then way back a couple of decades back, somebody made a joke over that this was named on the basis of a scientist who discovered it or who represented it, and his name was Forrest. So that was a joke, but then many people started using, and both the spellings are used, but single R Forest is preferred. If you see the Cochrane collaboration monogram, this is also a forest plot, right? And which is like everybody knows that whenever we open a Cochrane library. So let's see, come straight away to the talk of today. That what is a forest plot briefly looks like this. So now you'll see there are different columns. The first column, if you see, it's author and year. So if you go through a forest plot, this is the first thing that you see. How many studies? There will be an author and the year of the study. If you see the second, there will be groups. There will be two groups. For example, one is a control group and one is an interventional group, or there are two types of interventions. And here will be the results of those studies. The third will be the estimate of effects. So this is, if you see, you'll have a box and you'll have a line. So I'll come to this. What does it mean exactly? And this is the line of no effect. If you see there's a line running, this is called the line of no effect. So the line of no effect means if everything lies on this line, means both the interventions are equal. There is no difference at all. But if you see here, this is not possible that all the studies show that exactly there is no difference between intervention and control. So there you'll see that these boxes and these lines are spaced differently in different studies. So that is the difference between different studies, and you want to know that what is the exact thing. The third is the column is the weight. And now what does the weight means? It means the weight of the study. Now if you see, some studies have small weight, some studies have a large weight. For example, if you see the lowest is 9.78 and the highest is 31.72. Grossly speaking, this also means that how much impact or effect of that study has been given in this forest plot. Now, if you see this, the sizes of these boxes, they are different. Some boxes are small, some boxes are big. But the study which has the maximum weight has the biggest box, right? So the size of the box is somewhat refers to the effect of that study that has been taken, or the weight of the study that has been taken. Now see the smallest box here. So which is the smallest box? This is the smallest box here, right? And see the weight. Also, if you see, this is the smallest study in the whole entire group. 10 patients here, 8 patients here. If you calculate the total number of patients, it's 18 only. And see the boxes. So smaller is the study, less likely, less is the weight of the study, and also less is the precision of the study, right? If you have small numbers in a study, the precision will be less. And how will you know? Just have a brief look at this forest plot. Just have a look at the size of these boxes and the size of these lines. Larger is the lines, means larger is the confidence interval, less is the precision of the study. So if you want to talk about precision of the study, they will have, so suppose for example, this is the largest of all the studies, right? So in this study, the box is big, the lines which represent the confidence interval is small as compared to other. The biggest line is here in the smallest study. Means smaller study have smaller boxes, they have wider lines and less precision. And that's why their weight in the forest plot is less, right? If you give equal weight to this study also, then you won't have a good forest plot. Your overall results will be compromised. So that is the reason that different weights are being given to different studies. Study which is big, which is more precise, has been given more weight. Now come to the last column. So in the last column, if you see, you will have some figures. This is SMD, which means standardized mean difference. RE means random effect model. We'll come to this later, and 95% confidence interval. So this is the standardized mean difference, 0.11, and 0.64 to 0.87 is the confidence interval. The wider is the confidence interval, the less is the precision. Very simple. So if you see, this has a wide confidence interval, so you will see it ranges from 0.12 to 2.12, very wide confidence interval. And now see this bigger study where you have a big box, and see this has a relatively small confidence interval, or this has a relatively more precision as compared to other study. Now this is, if you see at the bottom, this is the overall SMD, the overall results that you represent. So I'll come to the other parts of this forest plot. These are heterogeneity indices, Q index. DF means degree of freedom. What is the degree of freedom? Nothing. Number of studies -1 is degree of freedom. That is used to calculate the heterogeneity between studies. What is heterogeneity? Heterogeneity means all studies are different. You assume that patients are different, age group is different, and in some studies the way of calculating success or failure is different. So P is the heterogeneity. If it is less than 0.05, it means there is significant heterogeneity, but this is not usually used. What you use is I square. I square determines, if I square is high, then there is high heterogeneity. We'll again come to that. And this is overall effect, which is called Z, which is 2.79, for example, in this forest plot, and this is 0.005. Which means that there is significant difference between these two groups, and whatever intervention, if it has been carried out, that is significantly more effective or less effective as compared to the other group. So this is the overall effect, which means if you see this overall effect with this diamond, which is represented as diamond here at the bottom, it lies completely to the one side of this line of no effect, right? So if it is overlapping with this line of no effect, which means that probably there is no significant difference, and then P will also be not significant. So if you see this diamond here, this diamond is completely to the one side of line of no effect, which is this straight line. If it is overlapping with this line, if suppose if diamond is one side, but still these corners overlap with this line of no effect, that means that probably the significant difference is not there between the two groups. So now again, just to recapitulate whatever I spoke in the first, this is the line of no effect. This line of no effect passes through 0 if it is a continuous observation. For example, you are observing weight between two different groups. Weight is a continuous value, and it's represented as weight plus minus standard deviation. For example, 10 kg plus minus 2 kg. So this is this line is going to pass through 0, because then you have an absolute 0 value. But if it is a dichotomous value, then it's calculated as odds ratio or hazard ratio, and this line of no effect, there will be a 1 here because it cannot be 0, right? So now if you see, this is the line of no effect, again standardized mean difference, and rest all values are same. Now again, just so yes, so this means that there are two groups of intervention. Which intervention is better? The goal of this forest plot is to find out. This is just a demo piece. We'll come to a real study where you find that what is the main goal. So this is just a demo piece to demonstrate what are the components of forest plots and how to interpret them. Then this is the box. We have already discussed that. And now these are the whiskers that we call them whiskers, the line which crosses across this box. So this represents 95% confidence interval. Just by looking at this, you can say that the confidence interval is wide or confidence interval is narrow. For example, the confidence interval is minus 0.64 to 0.87. So this is represented by these lines. Now coming to the, as I mentioned, size of the square is equal to the effect size is equal to study weight. So if you see this box, this has a bigger study weight, and this is the smaller box, this is a smaller study weight. Very simple. Now coming to again the same study weight and precision as correlated. So the higher is the weight, the bigger is the precision. So this is these two studies, if you see, good precision, small precision, and this is the final effect. This is the final outcome that we are interested in. So what is this is the overall outcome that we are going to represent when we are representing the results. Now this is the pool size, which is represented by diamond. Rest all is boxes. This is the overall effect. Means you have combined result of all the studies is represented by this diamond. Now this diamond, the corners are represent the 95% confidence interval. Suppose this is too wide, means a bigger confidence interval. So this is something that we need to remember whenever we see a forest plot. Now, should we use the mean difference or standardized mean difference? Both can be used, but standardized mean difference is used when the outcome is measured in different units across trials. For example, somebody is measuring in kgs, some studies are presenting their results in pounds. So now how to adjust the results of those studies? So there you can use standardized mean difference, because then the effect of different units is negated. Coming to heterogeneity, which is very important and which is presented in every forest plot. So how to interpret heterogeneity? It's either by visual inspection, or as I said, the wider is the confidence interval, and you can see the overall forest plot and see if the studies are looking similar or different. That can be done. If the confidence intervals are overlapping, this means less heterogeneity. If they are completely different, then they are more heterogeneity. And then some statistical tests which the computer will do itself. We don't need to calculate them manually. This is by chi-squared test, then I-squared statistics. So I-square is the most commonly used. Whenever you see a forest plot, just see what is the I-square. I-square ranges from 0 to 100%. Less than 40% not significant heterogeneity, but more than 75% means the studies are significantly different from each other. So let's see here. Now you see a lot of these are overlapping with each other. They are lying in the same line and they are overlapping with each other, which means that probably the heterogeneity is less. Just by looking at the forest plot, of course, the final interpretation will be by the statistical test that your computer will calculate. But just looking at the forest plot, you can assume that probably there is not much heterogeneity in this systematic review or meta-analysis by looking at this forest plot. Now look at this. Now here, if you see that there is a lot of overlap, and you will see that I-square is 0%. Means the heterogeneity is not significant and the studies are more or less representing the same outcomes. Now see this, they are widely separated from each other, and if you see that, you can just by looking at the forest plot, you can assume that these studies probably have a high heterogeneity and therefore we have to be cautious when we are interpreting the results just by looking at the forest plot. Don't need to see any stats also. Now let's revise what we have done. This is a real study from where we have taken this forest plot, and just to recapitulate what we have seen, this is from orthopedics, the total disc replacement versus anterior lumbar interbody infusion. What is the transfusion requirement, or what are the adverse events? So now you see these are the events, these are the total number of patients. This is group 1, TDR group, means total disc replacement group, and this is the second group. These are the number of events. For example, these are adverse events, or these are success rates, or these are whatever the outcomes, and this is the total number of events. Now these are the weights of the study. Again, if you see the largest study, which has 405 here patients, 172, has been given the large maximum weight, which is 51.3%, and rest of the studies, which are relatively smaller, has been given less weight. So this is somehow that a grossly a forest plot is seen. You can see that the final effect, which is represented by a diamond, is completely on one side. It's not crossing this line, which means that one intervention is definitely significantly different or more effective than the other intervention. So these are only, this is just a small system meta-analysis or forest plot that I am showing you, because just so that it will be easy. And these are the measures of heterogeneity. If you see, I square is 38%, which is not very high, less than 40%, means there is some heterogeneity, but not very high. Test of overall effect, Z, and this is again very significant, which means that overall one group is significantly different from the other group. Now this is the same. Suppose if you want to calculate the heterogeneity by yourself, this is just, you can calculate it by this formula. But again, this represents, now again, if you see, this is different from the previous forest plot, because here, if you see, the diamond is crossing the center line. The overall effect may be this side to some extent, and maybe that side. So which means that overall the results should not be significant. And if you see, the overall effect is not significant. P is equal to 0.15, which is not significant. And there is significant heterogeneity. One studies, the box is completely this side. One study, the box is completely on the left side, which means that the studies have significantly different values. And that is the reason that if you see the heterogeneity, which is represented by I square, is 87%, means there is substantial heterogeneity, and you have to address this heterogeneity when you are finally writing the paper, that why was there a heterogeneity? Was some study somewhat different? Did it include different set of patients? Should you have excluded? So this has to be explained. Whenever the heterogeneity is high, this has to be explained systematically in your paper. And that is why if this diamond is crossing here, it means that probably both interventions, you cannot interpret that one is better than the other, because this is crossing the line of no effect. So how to make a forest plot? It's just a small video that has been made. And first of all, you have to download the review manager. It's available online to download. And once you have downloaded this review manager, it's a very small software, it's not a big software, and you open it. Once you open it, you'll see these columns, and finally you start a new protocol. This is just a practical example that how to do it in real time. Once you do it, you just click next and see there are many types of different studies which we can do. But suppose we want to do an interventional review. So we do an intervention, click that, then click next on an interventional study, and we see that we want to compare intervention A versus intervention B. And we can name it any. Suppose we want to evaluate EUS guided biliary drainage versus ERCP guided biliary drainage. We are just going to compare these two modalities. What is the technical success between these two modalities? So we write it EUS versus ERCP for biliary drainage. So this is just a format that you fill in this software. This is available online, available for free. 1 month trial at least is free, and then probably there is some charge. So you click to the full review that you just want to do an analysis of, you have all the material available. Once you go to that, you just see these columns that where you want to click. Now you want to add studies here. So you have to pay attention on the left pane. On the left pane, you will see all the columns where you need to add the studies. So once you click that, you'll get all the references. Right now, we have not included any studies, so you just want to include studies. So you first click on the included studies. You'll find that there are no included studies, but now you want to add a study. So click on the add to study, and here you will find study ID. For example, you want to make a forest plot of 5 studies which you have included. So just include the studies, add the author, add the year, click next, and then finally in this way you'll be adding 4 to 5 studies. So this is just how you enter your data here and then add another study. So this way I won't be showing you all the studies. So this way you'll be entering all the studies. So we'll rapid fire it a little, and then once you have added all the studies, you finally come to what is the outcome that you want to measure here. So these are our two groups, EUS guided drainage versus ERCP. So this comes automatically, you don't need to do anything. You want to calculate the odds ratio, this is fixed effect. You can later on change also this, and finally click next. So here you click next, and this is all, you don't need to touch them. They are by default, they are kept like that. And here you want to see the graph. You want to label ERCP on the left graph, EUS on the right graph. This you can modify according to your own wishes, which means which side of the forest plot you want to keep, which group. So favors EUS, favors ERCP, you do it, and then finally you come to your analysis. So this is the basic thing that comes once you do it all. You'll have a blank graph. There is on the extreme right, if you see, this is a forest plot, but this is blank because you have not included any study, you have not included any data. So here what you do is now you include all your studies and start filling your data. So these are 5 studies that we have filled. You just add those studies here, and now you'll see that there are events, there are total number of patients. You just need to fill those. For example, we want to see the technical success of EUS versus ERCP. For example, 33 patients underwent successful ERCP, but 7 it failed. And in the other group, 31 out of 31 were successful. So you just fill all this data, and you will see that the forest plot will start appearing there. There will be some boxes which start appearing there. So this is something that you have to do manually. The data filling has to be done manually. And once you have done it all, you will see the total number and everything, all the total patients, total number of events, and you'll see the diamond and everything there. So this is just how to make a forest plot. Once you have done it, you can just open it and save this forest plot. Now you'll see these are the weight of the studies that we have seen in our previous demo forest plot, but this is something which is like we are doing in real time. So once you have done that, I think you can proceed and look at your forest plot, that how does your forest plot look. So you have also the option of enlarging the forest plot or reducing the scale of the forest plot. That can be done easily in real time. So this is when you click, how does your forest plot looks. This is the forest plot that we just made. So it takes not more than 10 minutes to create this forest plot. Now, if you look at this forest plot, you see that the diamond is completely towards the left. Left is what we have kept as favors EUS guided biliary drainage. Right is favors ERCP. So that our result shows that the diamond is completely on the left. It favors EUS guided biliary drainage. What is the heterogeneity? Heterogeneity, if you see, it's small, but it's not significant. So we can interpret this forest plot and any other forest plot by this. There are multiple other options there that you can always click on and see if you want to add. This is the calculator there, and you can also calculate. I'm not going to show this because this is not required for majority of the studies. If you want to exclude some study, you just have to click one of the studies which has to be excluded. Suppose you want to exclude one study which is outrightly different from other studies, and you want to do an analysis without that study, you can just click on one of the studies and do an analysis, you will have the analysis of 4 studies out of 5 studies. So this is the practical way of doing it. I think if you have RevMan Manager, which is free online, it can be done in no time. So there are online tutorials as well, which can be done. So this is the new version. If you want to buy the latest version, I think it's a paid version, unless 2022 it was free, but still you have 5.3 version, which is free online and which can do most of your job. It can also be done in Microsoft Excel. I don't do it because it's not ideally designed for that, the Excel sheet. But if you want to do it, then you have to go through Meta Essentials, which is I think available for free. The other ones are also paid. CMA is a very good software. I personally use CMA also, but since it's very costly, it costs like 25 to 26,000 bucks for 1 year. I use it for many of my meta-analysis, but then this is a paid version. If you want to use CMA, then it's also very easy. Remine is something which you can use for free as of now. So regarding construction and interpretation of forest plot, if there is any questions, I'd be happy to answer. So Z is the overall effect. So if you see online, you will get the Z tables. Means there is no rocket science there. If you see Z is 3.2 here, and if you type online that I want to see that this Z value means significant or insignificant, that can be seen from that table. So there is a table online, but then since computer is calculating for us, Z means whatever the pooled effect is it significant or not? For example, one modality is better than other modality or not. So if Z is less than 0.05, it means significant. If it is more than 0.05, it means probably both modalities, there is no significant difference. So any component of forest plot, if you feel that there is something that you want to ask, you can ask. Since it was just to see the components of forest plot and how to construct a forest plot. The best is RevMan if you are comparing two modalities. Easy, very easy to fill, and in 10 minutes you can complete the analysis if your typing is fast. Anything, ma'am, from your side? So this is yes. So this is done by the software itself, and basically it's roughly correlated with the size of the study and preciseness of the study. So bigger is the study, more is the sample size, more is the weight allotted to that study, because it's likely to be more precise than smaller studies. Suppose I do a study with 1,000 patients, it will be included, and somebody has done with just 50 patients, it will also be included. So now, but 1,000 patient study is likely to be more powerful and better than the 50 patient study, because it's likely to include the sample population in a better manner. So there they allot more weight. If you allot equal weight to both the studies, then it seems like you are doing injustice with the bigger study, which is more precise. So they allot a weight. There's a calculation technique for that, which they do it. The software will do it itself, and then allot a weight to the study.
I've been asked to peer review for ASCO education book. So they will be sending the articles to be published in ASCO education book. So do I have to do all these things, or just to see the merit of the pick to be entered into the ASCO education book, or what I'm supposed to do?
ASCO
As a
education.
peer reviewer.
As a peer reviewer, okay, if you are a peer reviewer and you are reviewing a article with forest plot, right?
Article is sent in the I'm supposed to send to editor whether this article is
Worth publishing or not? Yes, very good point. So now the first thing you have to remember is, suppose a forest plot has been created, like this is a forest plot using only 3 studies, right? So there are many statistical tests which can be done, but their accuracy is seriously compromised if the number of studies are less. Ideally speaking, less than 10 studies, the strength of that review or that meta-analysis itself is compromised. And then you have to see the heterogeneity of that study, and if the author has addressed that. For example, this look at this graph. Is it visible? Yeah. Look at this graph. So their heterogeneity is 87%, right? And the paper, the author, main author of that paper has not commented anything on this heterogeneity. He just wants to escape from that heterogeneity. It's 87%. It's very high. What's the reason for this heterogeneity? Why the included studies are so different? Why the results are so different? So you have to ask that author. The first thing is that how can you explain such a high heterogeneity? Did you do a sensitivity analysis? Now, sensitivity analysis means you exclude each study one by one and see if this variation reduces or not, and do the complete analysis. For example, you have 10 studies, you do it with 9 studies, then 8, then exclude each study one by one. So heterogeneity has to be addressed. The size of the number of studies that have been included has to be taken into account. And if he has done an analysis, these analysis where the number of studies are so small, then you can always question that you cannot be assured with such small number of studies, and probably you should wait till more number of studies are there. For example, if I have to comment on this review, heterogeneity is high, I'm not happy with it unless you address it, right? Unless you explain why the heterogeneity or I square is more than 80%. So there are many comments that you can, of course, you have to see the entire paper. Just by looking at one forest plot, no study can be accepted or rejected. There are entire things that have you to see, and there are many components of review. So forest plot is just one of them, which you have to take into account before you give interview. But this forest plot can be interpreted as, look, these are the problems in this forest plot. So I don't agree with the interpretation.
He'll be sending only his study, no sir. So we have to observe his study versus the standard of care forest plots you mean.
So forest plot means you have used, this is mainly for systematic reviews or meta-analysis, where they have analyzed 10 studies, combined them, and then created a forest plot. So that's how a forest plot will be created. This will be for systematic review and meta-analysis, not for individual studies. Yes. So dichomotor, if the answer is yes or no, for example, technical success, yes or no, there will be different. It will be an odds ratio or something, right? Hazard ratio, odd ratio, or relative risk. If it's a continuous variable like weight or temperature, then there will be like it will be a different. So the outcome here, the effect will be different. Mean difference means it's a continuous variable. Odds ratio means it's a so this is not exactly meant to see time to event thing. This is just for category. So there are many times we see forest plots, we get amazed by that, but we don't, we are not able to criticize that forest plot and dissect that forest plot. That what does this forest plot is revealing? But that forest plot itself in the entire paper can give you the exactly all the information that you require from that study. So for example, just looking at this, I'm convinced that these two interventions are not significantly different, although everything is to the right of this line of no intervention. But when you see the overall effect is not significantly different. So I'm convinced that both are more or less similar. The patient can choose either of the interventions, right? But just looking at the first, I don't see the whole paper. I don't see the conclusion and anything. This is, if the author is biased, he can say that, look, the main diamond is towards the right of this line. No. See, the overall effect is 0.15. The diamond is crossing the line of no effect. That means that both interventions are, everything is possible. This also possible and that also possible. So no way that an author can definitely conclude that. If he has concluded, then we can give a comment that how can you conclude this. So the size of the diamond exactly does not signify, because there are more than one diamonds, then we can say that one diamond is larger than the other diamond. The center of the diamond means the overall effect. For example, you see that 60.8, the mean difference, the bottom column. You see the figure of 60.8, right? So the center of the diamond means 60.8. And if you see, just see the graph also, you can see from 0 to 100 and probably it lines somewhere around 60.8, right? So center of the diamond represents that. The sides, the corners of the diamond represent the confidence interval. Minus 21.9, you see the diamond is crossing the line of no effect, and to 143.4, which is towards that, the extreme end of the diamond, right? So each study must be having some or the other problem, right? And if you see that, look, there are so much of heterogeneity to find out the studies. For example, what I do is I have 20 studies. We do poem for achalasia. Some centers are showing very good results, some are showing not so good results. So we adjust, take it out in different ways. First of all, we analyze like each country, let's say Asian countries, Western countries, and do separate analysis and see if now the results are mattering. Some have included older patients, some have younger patients, separate both. So this we have to see critically, that why there is so much heterogeneity in the analysis. Although everybody is saying, all the studies are saying it's a good treatment, but then there is so much heterogeneity. So there must be something that we are missing in the analysis.
Each of the adjustments you prepare a forest plot and you.
We can, because on a click we can prepare. You can just exclude that study by clicking it and unticking it, and you can see the results. So suppose one study says that poem is successful only 60% of the times, rest all say 80 to 90%. So we can exclude that study and say that, look, this was the only study. Probably the author was not, the operator was not experienced. Probably the patient group was more advanced. So that is how you can explain, but you have to explain, give an explanation why so much heterogeneity.
Of studies, certain studies. It
So-
depends on the author or
So-
any set guidelines.
So, which studies you should include and which you should exclude. So, you have, before you start a systematic review or meta-analysis, you provide some inclusion and exclusion criteria, that I will include only studies which have patients more than 18 years, who are less than 80 years, or who are not pregnant, and then who don't have this disease, that disease, and where it was successful. So, you have some outline criterias when you start extracting the studies. All those studies should be there, but suppose some study has not provided the result in the way it should be provided. Some patients, some studies give you exact term that, okay, the ICARD score after doing a poem, patient's ICARD score was 3, and some studies simply says that there was no dysphagia. So that study cannot be included, and you give a reason why you did not include that study, because you had nothing to measure there. They should provide some measurable outcome, and those outcomes grossly they should be more or less in the same manner. Otherwise it is difficult to summarize all the effect.
Confidence interval or
No, it should never be done. That you can make a argument that I redid the analysis by excluding very small studies. So when you are doing it and selecting studies, you should make strong recommendations that I will not include small studies because it will bias my results. Because small studies are, of course, not very sound. That is something that can be done. So if you see the outcomes here, this is the outcome of 4 studies, the cumulative outcome of 4 studies. So if I see only these the top 4 studies and don't see the diamond, I will be biased to say that probably this one is the right one, is more better therapy, not the left one, because everything is going towards the right. But then final diamond, which is the actual outcome, which represents the Z value, that is the one which has to be seen. And see, even if you don't see the diamond and you see the top three graphs, the three of the studies, the lines are crossing the line of no effect, which means that probably these are the studies which say that 3 studies out of 4, they say that the outcome can be anyways. So just looking at the way you look at the forest plot, if you refine that way, then you will be like interpreting just by seeing this and say that no, I don't think this is. And you can see the diamond how much it is close to the line of no effect. If it is very close, then probably there is more research required. If it is very far, it means that no, there is no doubt that this one is much better than the other intervention. Because of the wider confidence interval. Yes. Yes. If suppose if the diamond is the confidence interval is very large, the ends of the diamonds will be very large. So I think it's yes. So Partha should be the next.
About after this talk. My screen visible? So today we shall discuss survival graphs and give some practical examples. How this name survival graphs came? It actually originated from cancer studies, which actually evaluated the survival of oncology patients who survived on either without therapy or on specific therapies. Specifically, most of the studies started on children with leukemia. So today's learning objectives are to understand the principles of survival analysis, to be able to interpret the results of different survival analysis, to understand the concept of hazard ratio, and to be able to draw nice KM curves and calculate the hazard ratio. So what are the principles of survival analysis? I don't like this name survival analysis. I more like this term time to event analysis because that only specifies those earlier cancer studies, but this could be any event which can be evaluated over time. Like this, in this case, this is one of the first studies which we published actually on this time to event analysis, which actually evaluated the risk of stricturing disease in patients with Crohn's disease if the diagnosis is delayed beyond 12 months and compared to patients who have been diagnosed before 12 months. As we have seen, the chances of stenosis and surgeries were significantly higher in those who had a delayed diagnosis after 12 months of disease. Whereas in case of fistula, there was not significant difference. So you have to frame your research question first. There should be two questions: when and whether. When the event occurred and whether the event has occurred, yes or no. So event can be anything. Like in our previous studies, we compared whether the patient with disconnected pancreatic duct develops more recurrent fluid collection as compared to those with a normal duct, or we have seen patient with Crohn's disease with a family history as having higher risk of biologic use compared to who don't have a family history. So event can be anything. It need not be a death, which was originally in the survival studies. It can be any fluid collection, development of diabetes, any outcome like hospitalization, surgery, or any outcome. So why not do a linear regression analysis? Because say suppose if you get two groups, some of the patients will develop an outcome or does not develop an outcome. We can do a linear regression, but why don't we do that? Because this data is often not normally distributed. I will show you the example. Say for example, few patients may have a follow-up of more than 10 years and few patients which have been included have only follow-up of 1 year. Still they can be included in time to event analysis. So that's why it is not normal distribution, though that's why this linear regression is not used. Then there are two concepts. One is censoring, another one is staggered entry. I'll discuss what is that. And always there may not be a multivariate regression. So this is the first paper that came from the Kaplan and Mayer, from which the Kaplan-Mayer name came. That was from the University of Chicago and University of California in 1958. they showed this non-parametric estimation of incomplete observations. Like some patients may not develop outcome like diabetes over a period of 5 years. If you follow the patient for 10 years, they may develop a diabetes. So those non-parametric estimation from incomplete observations, they first published this statistical method how to calculate that. So in this survival analysis, there may be survival time. I showed that the survival time may be non-normally distributed, like non-parametric. Like in this survival table, as you can see, case 4 to 14 has only 6 months of follow-up, whereas the mean follow-up is 48 months, whereas few patients have only 3 or 6 months of follow-up. So that's why it is not normally distributed, but still they can be included in those studies. Then censoring is a unique thing in survival analysis. Censoring is say for example, a patient is lost to follow-up after 6 months. You don't know the follow-up, but still that patient can be included. Next, the probability of event can occur after that. Like a diabetes, we are evaluating for diabetes and outcome, but you are following only for 5 years. Diabetes may develop after 10 years as well. So this is called right censoring. Or there may be left censoring, like while you are starting the follow-up after the starting point, it may be 6 months later. So you may miss that part, the initial 6 months. So this is called left censoring. And different events, some event may occur which may the patient may not be eligible for this study. I'll show you an example. Right? For example, this is a study that we have done for disconnected pancreatic duct versus normal pancreatic duct who develop diabetes. Only 20 to 40% develop diabetes over a period of 5 years. But some of the patient may develop diabetes after that period also. But that is called right censoring. So we need to follow that patients further, but still those patients can be included in the study. Then left censoring, usually in patients with Crohn's disease who underwent go a surgery, we usually follow up them at 6 months. They may develop a recurrence before 6 months, or sometimes after cancer surgery, the patient first follow-up time maybe at 3 to 6 months. The patient may develop a recurrence before 6 months or 3 months itself. So this is called left censoring. So, and also there is censoring due to loss to follow-up. Although when you see a Kaplan-Meier curve, always you should ask, if you are as a reviewer, you should always ask what is the number at risk. As you can see, although the total time here is 120 months, that is 10 years in this Kaplan-Meier curve, you will think that all the patients have a 10 years follow-up, but it is not like that. If you go by the number at risk, the number of patients who are follow-up at 100 months is only 5. So always, if you are reading a Kaplan-Meier curve, always ask for this number at risk, because even a patient who have only 3 months follow-up or 1 month follow-up even can be included. So that's why that is important to have the number at risk. And there is another factor like internal censoring. This is important. I have experience because one of my papers got rejected in a big journal because of this factor. Because what happened, we actually evaluated the effect of curcumin in patients with ulcerative colitis as an adjuvant treatment and evaluated the patients at 3 months, 6 months and 12 months. But what happened is patients, we evaluated for clinical remission, clinical response and endoscopic remission. But what the reviewers comments was okay, but editor said that there is a statistical flaw. Like you are evaluating at 3, 6 and 9 months, but the clinical relapse can even occur in between as well. So you should have a more frequent monitoring policies. For example, which has to be monitored. Like diabetes, we have to have a short monitoring interval. For example, few outcomes like surgery or hospitalization, you need not monitor as well. So this is called internal censoring. The patient can come in or out of the observation. So that was the editorial comment. That's why it was rejected that time. So some events are obvious, like time to surgery, death, hospitalization, symptomatic fluid collection, recurrence. These are obvious. But clinical remission, if you don't ask the patient at different points of time, then you may miss that. Development of fluid collection, you may not know, it may be asymptomatic. New onset diabetes, you don't detect that particular intervals, you may miss it. Then another occurrence of another event may occur, like a patient with ulcerative colitis, the patient may undergo a colectomy. Then you may not evaluate for a relapse. So some event may occur, then this patient, the last follow-up should be at the time of the colectomy, not the total follow-up. And there may or may not be explanatory variables. Like in the right-sided example, they are comparing disconnected pancreatic duct versus normal pancreatic duct for recurrent fluid collection. There are no explanatory variable. For example, for the same two groups, if we see for new onset diabetes, there are several other variables like age, gender, BMI, family history of diabetes, chronic pancreatitis, etiology of pancreatitis, which can affect this curve. So those covariates has to be evaluated in that. Then I told about another principle, that is staggered entry. Say for example, this is our IBD registry. The first patient was entered at 2004, and the last patient that was entered in this study was in 2017. So anytime the patient can enter. If they have a little bit follow-up also, you can take the patients. So that's why in the most of the retrospective studies, this has been included with a larger follow-up. So staggered entry is allowed anytime in the study. You can the patient may enter. So these are the prerequisites. You should define the event, define the time scale, origin of the event, and T is a random variable, and chances of event should be equal between the groups. I'll discuss all of them. Say for example, you defined recurrent pancreatic fluid collection. In our study, we defined as pancreatic fluid collection more than 4 centimeters, because 1 or 2 centimeter residual collection may be normally there. You should define new onset diabetes, whether you are diagnosing by fasting blood sugar or both fasting PP blood sugar or HbA1c. The definition should be clear. Then the time scale. Here the time scale is not mentioned in this curve, whether it is weeks, months or years. Then the origin of the event, whether to calculate from the day of the drainage of fluid collection or from when you remove the SEMS, then from which should be the origin of the event. Or for a patient with IBD, whether you should take the time from the day of the symptom onset or you take the time from the diagnosis. All these are important. So you should define what is the 0 point in this time to event curve. Then time is a random variable. This can vary from 0 to infinity. So chances of occurring events should be equal. Like in the right-sided example, you can see the blue curve is flat. In that, we have compared recurrent fluid collection in disconnected pancreatic duct versus who have a normal pancreatic duct. This is not these two groups don't have equal probability of developing a fluid collection. Whereas in the left-sided curve, developing a new onset diabetes are almost equal between the two groups. So that how can you know that? There is a log minus log curve, which I will show the different methods of survival analysis: log rank, Breslow, and Taron-Ware. So which one to use? So there should be a proportional hazard assumption. Usually, if the hazard function, if they coincide or intersect with each other, or they go away from each other, like in the right-sided example, then the hazards may differ over time. So the comparison may not be appropriate. So how to use it? You can do a log minus log survival plot in the Cox regression model. I'll show the example. If both the lines are parallel in the two groups, that means the chances of the hazard is equal in all those, and these two groups are comparable. And if, say for example, if log-rank test performs best at the right side of the curve, whereas the Taron-Ware test performs best in between, whereas the Breslow test picks up early difference very well. So if the lines are not parallel in the log minus log plot, log-rank gives inflated type 2 error and with loss of power. So how the survival calculation is done? This is complex. They calculate the probability of survival at 1 month and 2 months and multiply. Whenever they are calculating at the unconditional probability of survival beyond 2 months, they multiply this two, and how this is being calculated in the survival plot. So whenever you are doing just a log rank plot or Kaplan-Meier analysis, you will get a log rank statistic. But it is not if it is only statistically significant if the x square is more than 3.84. It is not similar to the odds ratio. Then before this analysis, you should do a timetable analysis to see whether a particular event is occurring in a particular period of time. I will show an example in which if you see recurrent fluid collection, most of the recurrent fluid collection occur in the first 3 to 6 months after the drainage procedure or whatever it is. After intervention, first recurrence occurs in the first 3 to 6 months. So you divide the events within every 3 months intervals and see which is the period where most of the events have occurred. So here are two things are there. One is probability density, that at that point 3 months, how many events have occurred, that is the density, and the cumulative proportion surviving at that interval means have not developed the outcome. So the probability density is divided by the cumulative percentage which are surviving to calculate the hazard ratio. That is how the hazard ratio is calculated. So the cumulative probability by the probability density at the point of time is used to calculate the hazard ratio, that is calculate the dynamic speed of an event that is occurring. So interpreting a life table, that I already told, that whether the event is occurring particularly in a specific period of time. So these are the prerequisites. There should not be any covariate. Then you should do a Cox proportional hazard analysis rather than a Kaplan-Meier curve only. Then staggered entry allowed, but all cases should have equal probability. You should do a log minus log survival curve to see whether the probability is same. Then censored and uncensored case should have equal probability of the event. So that's why this actually study shows in acute leukemia patient, this evaluates 5 types of chemotherapy regimens on the left side, the survival of those patients. Whereas other variable like WBC count, they have stratified into 3 groups, and I've seen that also affects the survival. So this is one of the covariates which can affect the survival. So you have to take the covariate into account. That's why this Cox, this is the first paper that is also in acute leukemia patients which have been treated with 6-mercaptan purine. They have calculated which covariates can actually influence this time to curve analysis, time to event analysis. So this is the example of Cox proportional hazard ratio, in which this is an example that data sheet that I have shared also is this only. The dependent variable is the final event, that is the time to first intestinal resection or the first surgery. And the independent variable, we want to study the effect of family history of IBD, whether that is affecting the time to first intestinal resection or not. So these are the 2 variables, but there are few confounding variables like age or diagnosis, gender, smoking, which can affect the time to first intestinal resection, biologic use, disease behavior at diagnosis, the location of the disease. So that's why whether multivariate Cox regression analysis is required to identify whether this family history is an independent factor which can affect the intestinal resection or not. So this is the example. Here I have plotted the time here and the different covariates here, and going to the first to the life table, then putting the time, that is the overall time of follow-up for the patient who have developed an outcome. The time of outcome will be inserted into the Excel. Then I am dividing the intervals, that is up to 240 months follow-up was there, almost 20 years. So I am dividing it by every 3 months up to 240 months. So that will show the live tables every 3 months what events have occurred. So then you get this kind of this thing, that how many are surviving, and also you can calculate the number at risk. For if you calculate the Kaplan-Meier curve, you will not get the number at risk. From this table only, you will be getting the persons which are surviving at the end of each interval, and from this table only you can put that numbers in that how many patients are at risk at each point in time. Then that is the probability density, and what I already told, and that has been and also the cumulative proportion surviving at each time point, that is used to calculate the hazard ratio. Then again going to that, then calculating the Kaplan-Meier curve, drawing the Kaplan-Meier curve, putting time to surgery in the time, and then status, whether the surgery is done or not, putting the value is 1 if the surgery yes or no. Then the factor is family history, whether that affects it or not. Then putting the log rank test, then calculate, and it will show stratified based on this. Usually there will be survival time, 1 minus survival time and log survival time. I usually use 1 minus survival time, that usually shows from 0 how many events are occurring. For cancer studies, how many are surviving is important. For our studies, how many are developing the event is important. So that starts from 0, whereas the other starts from 100 and decreases. So here we get the plot. This is the live table that it already makes, but that is not important. So this is the log rank test. This p-value is 13, but that means it is more than 3.48, so it is important. So as you can see, there is significant difference between the patients who had a family history to having more intestinal resection. But there may be other covariates as well. So you can both draw a survival curve or a 1 minus survival curve or a log minus log curve to see whether the proportion, the risk are same between the 2 groups or not. I'll show in another example. Then I'm going to the Cox regression model. Then if you stratify by family history and define the range here, 0 and 1, that is the family history present or absent. Then this is the curve, that is the patient who have developed family history or have family history or don't have family history. This is the survival curve. Whereas if it start from 0 and goes on the right side, it builds up on the right side, that is a 1 minus survival curve. Then going to the Cox proportional hazard analysis, the main factor is the family history, the surgery yes or no, and these are the covariates: age, gender, Crohn's disease extent, family history, and these are the factors. So you put which are the categorical variables, and usually you change. The first is 0, means 0 should be the baseline and 1 should be the comparator. So I have changed that. And then plots, I'm putting 1 minus log plot and separate line for, I want a separate line for the family history. Also, I'm drawing the log minus log. Here you can see whether the risks are equivalent or not. Also the hazard, drawing all of them. Then options, you put 95% confidence interval, you will get the multivariate analysis as well. Then you put OK. Then you get the results. This is the multivariate analysis below. And here is the difference between the two. Even after doing Cox regression analysis, family history was a significant factor. It was statistically significant between the two groups, means family history is an independent risk factor for intestinal surgery or resection. So you have to account for those covariates as well while doing those analysis. So I'm not going into these details, just wanted to highlight one point, that if you here, one of the covariates may be age, and that may be an independent risk factor for diabetes. Say for example, age more than 40 is an independent risk factor for diabetes. If you put that as a covariate, that may introduce bias, because that is a time to event analysis. You are putting another time this thing in the covariate, that may put a bias there. So you should be careful about that. So the take home messages are: frame 2 questions for your survival analysis: when, the time, and whether, yes or no. Most data are right censored, like most of the event may occur after the last follow-up as well. Define the event and the origin point and the time scale. The origin point definition is very important. Cox regression analysis depend on proportional hazards assumption, that both the hazard is equal into both the groups, and that for that you have to draw the log minus log plot. And KM only compares dependent and independent variables, that is Kaplan-Meier curve. But if you have covariates, you have to do a Cox proportional hazards and a multivariate analysis to account for confounding variables to assess whether the factor you are considering is an independent risk factor for the outcome or not. And the time dependent covariate like age may introduce a bias in the Cox regression analysis. With this, I would like to conclude my talk. Thank you so much. Any questions, I would be happy to answer that. Yeah.
Rare diseases or smaller studies.
Yeah.
How to go about
Yeah. So this is a very good question. So for that number does not matter here actually, because I have done a Kaplan-Meier analysis that has been recently published. I had only 20 patients in each group. I have I actually did a matching of the 2 cohorts. Only that has 20 patients in each group and only 1 year of follow-up. Any kind of follow-up, that follow-up may be as short as possible. Even a 10-20 patients, if there is significant difference, it will show up. That doesn't matter. Not even the time. If the time is very short, you may stratify into weeks as well. The time into weeks, or that 12 months you can break into months or weeks even. While you are putting the data, you can put in days as well there, so that it will be more broader and more neater Kaplan-Meier curve. And numbers does not matter. The curves may not be very good, but if there is significant difference, it will show up. Any other questions? So here, although this these curves look very good and very good for publication, and actually in 1/3 of my publication I have used these curves. So these are very catchy for the reviewers to understand, but you should always see whether the number of at risk is there or not, and whether the other covariates may be there which may be influencing the factor or not. These two things you should see, read between the lines in a paper while you are evaluating that. No, I showed the life table. No, when you are putting that life table, you are putting the total duration. Say for example, in this example, it was 240 months, like 20 years. 240 months by how many months you want the stratification. You can put 3, so it will show 3, 3, 3, 3, or you can put by every year 12. So it will divide that by every 1 year how many outcomes have occurred or how many patients are at risk. The table will show. So before that, this one I would always do the life table analysis to see how many are at risk at each point of time. Then you can initially do the log minus log. If the log minus log is showing that it is convergent or divergent, you can see that the risk may not be equal in between the two groups, and that's how you can analyze. Yeah, hazard ratio, I told that whenever there are multiple covariates, say for example, for an outcome, you are evaluating one of the factors. Your relation between two of the factors you are seeing, whether they are different or not. But there may be another factors which may be affecting that. Like in this example, risk of surgery in a patient, we wanted to specifically see whether family history is responsible for increased risk of resection or not. But we have not evaluated other factors like whether the patient is getting biologic agents or not, whether the location of disease in the small bowel, they will have a more risk of surgery, or the age of the patient, because the younger age of the patient maybe had more risk of a severe IBD, or the gender of the patient. We have not evaluated that. So in the Cox proportional hazard, we have put all those into the covariates as a covariates and divided it according to the categorical variable or a continuous variable, and then put it into this one, and that will show a regression analysis where you will get the confidence in 95% confidence interval, the hazard ratio, as well as the p-value, each of the factors, and whether they are independently associated with the risk of this or not. You will be able to understand. Not only the this one. Is it visible? Not in the presentation mode, but we'll start it. You go there, then you put this is actually much later. It is not here. It will not show here. It will show in the results, the output. Yeah. When you are putting the Cox regression analysis, the output it will show up. Output will show up. In here, it will show only the hazard function at each point in time. What is the hazard? Yeah. When you are putting the Cox regression analysis, then you see the output, and there you see the multivariate regression analysis. Whether there you can draw with any of the curves. Say for example, I only wanted to draw the curve of intestinal resection compared to family history. Someone may draw the curve of see the effect of gender into that, or not. It is quite later on. The last I showed. I'll show you maybe. In the last it is there. Almost 4 minutes video, so the last, not in the beginning. Right? The same things are there, but there will be another column for putting the covariates. You put the covariates, you go into the options, put into 95% confidence interval, and then it will come. You will get all of them. Here in the Kaplan-Meier, you will get a statistic, log rank statistic, but that is not. That is usually what don't report that. That is not the odds ratio. Usually only report the p-value while you are doing the Kaplan-Meier curve. Don't report the log rank statistic or whatever it is. Only the hazard ratio, if you have calculated based on multivariate analysis, then only you can tell that this is the hazard ratio or this was the confidence interval. For Kaplan-Meier curve, only the p-value has. You can report the log rank statistics was this. If it is more than 3.8, I told that it is significant. The reviewer may understand or knows that. This is the only Kaplan-Meier curve. The last one I showed the Cox regression analysis. This is a survival table. In the here the log rank statistic is there 11, and this is the only the Kaplan-Meier curve. But here the only you have to report the p-value. The upper one was the 1 minus survival, and this is the survival plot where it starts from 100 and goes to 0. Now the live table, and then last I showed this one. Here it is total 240 by 12. Here you can do the live table analysis and also and see and calculate the number at risk at each time point. Now I think I'll show this one. Again, I went to live table because I wanted to evaluate the family history factor. Any other question? Otherwise, I'll conclude. We'll just come and show. This is the same thing. This is a table from which we'll get all those informations. Number at risk and what are the patients which are developing the event within a particular point in time. Now here if you look, this is the survival plot. I'm going to the Cox proportional analysis. I'm putting the time into the last follow-up into the time, then going to the what is the outcome, putting the outcome, that is the surgery, and putting the age, then gender, Crohn's disease extent, all those family history, all those factors into the covariates, and then going to the whether these are categorical variables. Age is one of the only one factor which is a continuous variable, so it will be there. And usually you make everything the first because 0 is the first letter which comes before 1, so 0 is considered as the reference value if you do that. Then here you will get the log minus log plot, 1 minus survival plot. Here I want to draw the plot for family history. If you want to draw the plot for age, you can put age here and then continue, and then put in the options, I put confidence interval, I put correlation of estimates, and I want to see the last step only. Now I don't need to see all the steps. Then I put OK, and here it will come. Here in this results, here it will come. Yeah, in that it just above it went. All the 4, it will come as just a multivariate analysis. It will come like that. But this shows that it is independently associated with this. Even after adjusting for all the covariates, that remains significant. Anything else? Clarify more? Thank you. This I would like to conclude. Thank you so much.